In the last lecture, we discussed about the WKB approximation method, and we introduce the definition of WKB approximation method. It is used to calculate the approximate solution for the time independent Schrodinger equation, and we can also calculate by using WKB approximation method the bound state energy of a system, and we can also calculate the tunneling rates. And then we describe about the classical and non-classical region, and we consider a particle which is moving along an x direction, and for that particle we calculate the time independent Schrodinger wave equation. And we introduce the wave function psi of x is equal to a exponential k power plus minus iota kx, and the momentum k is equal to 2m into e minus v square root divided by h cut. In this system, and today we are going to calculate the classical region. In a diagram, in this line represent the potential, in this line represent the x direction. When the energy is less than the potential, this is a non-classical region, and this is a classical region in which the energy of particle is greater than potential. And this is the point where the energy is approximately equal to the potential. So we are going to calculate the time independent Schrodinger wave equation for the classical region. In a classical region, the energy of particle is greater than potential. This is time independent Schrodinger wave equation minus h cut square divided by 2m d2 psi divided by dx2 plus into v and x psi is equal to e psi. This is equation number A. In energy, we know that p square divided by 2m plus v. This is equation number B. Put equation B and equation 1. We will get p square divided by 2m plus v into psi. Vx will be cancelled with v into x psi, and we will get minus h cut square divided by 2m d2 psi divided by dx2 is equal to p square divided by 2m. 2m cancel with the 2m. Here we have the psi, so d2 psi divided by dx2 is equal to p square divided by h cut square. This h cut will be divided both sides, so we will get the minus p square divided by h cut square into psi of x. This is the Schrodinger equation. This is a Schrodinger equation. This equation and this equation both are same. Here the momentum p into x is equal to 2m into e minus v into x square root. This is the value of momentum. For this system, the wave function psi into x is equal to a exponential k power iota pi into x. This is the wave function. A is the amplitude, phi is the phase, psi is simple wave function. Phase is the quantity which describes the motion of a particle. This is a wave function psi into x is equal to a exponential power iota phi x. You will take the derivative of 2 times of this wave function, and then that value will be put into this equation. Simply, we know that this is complex function, so we will get the two values, one is real and imaginary, and the other is imaginary. So in the figure, we are simply calculating the classical region. Here is in this point, the energy is approximately equal to V. What show this point? If we put the value of energy is approximately equal to the potential, so if we put instead of energy the potential, so V minus V, this will be 0 multiplied by 2m square root, so this will become 0. If the momentum is 0, then the P is equal to h cut k is equal to P by h cut, k is equal to 0. It means that de Broglie wavelength lambda is equal to 2 pi divided by k. If this is equal to 0, so de Broglie wavelength will be 2 pi divided by 0, and this will be infinity, which is impossible. So this point is called the failure point in WKB approximation method. This point is failure point in WKB approximation method. So for the classical region, the function psi of x is equal to a exponentially over iota phi x. A is the amplitude, phi is the phase. Amplitude A of x is not constant, this is variable. It can vary, it can change. So taking derivative with respect to x, d psi divided by dx, we are going to take the derivative of this wave function. So psi of x is equal to a exponential over iota phi x. This a is vary with respect to x, so the derivative will be, this is first derivative of second exponential over iota phi x, this is the iota and phi prime x, plus this is the second function, and this is the derivative of first a prime into x. Now for psi prime into x is equal to a prime x plus a into x iota phi prime x is exponential bracket exponential over iota phi x. This exponential over iota phi x is common in both, so this we are taking the common exponential over iota phi x. Now derivative, now taking the second derivative of this psi prime, so this psi double prime will be equal to, this is the first function, we simplify this psi, so this is the first function, this is the first function, and we are taking the derivative of second, so exponential over iota phi x, then again we will apply the derivative, so iota constant phi prime x plus this exponential, this is the second function exponential over iota phi x, we will take the derivative of this function, so a prime x will be a double prime of x plus, here we apply the product rule again, so this will be the iota, this is iota, this is a first, then second derivative of phi prime x, derivative of second plus iota, and the derivative and the second function and the first derivative. So this whole equation we can write that a prime iota phi prime this iota pi prime x is multiplied with this. So iota a prime phi prime plus this is a iota multiply iota square, pi prime x is multiplied pi prime square, plus this is a double derivative plus iota ax this is iota a pi double prime plus iota pi prime a prime into exponential power iota phi x. This is common. So this will be a double prime plus a iota phi prime and a iota phi prime. This will be 2 iota a prime phi prime plus iota a into phi double prime minus a into phi prime whole square. I convert this function. This is this instead of this a into iota square pi prime square. Put equation 1 this is equation a. Put this equation a in equation number 1. d2 psi of x divided by dx2 is equal to minus p square divided by h cut square psi. So we will get this value. Now separate the real and imaginary part. So a double prime into minus a pi prime whole square, this is a real part and these are the imaginary part. I am taking the real part. So this is a double prime minus a into pi prime whole square is equal to minus p square divided by h cut square into a double prime is equal to a pi prime square minus p square h cut square into a. Taking amplitude a common, pi prime square minus p square divided by h cut square, bracket, dividing a both side. This will be a double prime divided by a is equal to pi prime minus p square divided by h cut square. So a double prime divided by a is nearly equal to 0. Then pi prime will be equal to p square divided by h cut square, pi prime square, taking square root both side, so pi prime will be equal to plus minus p divided by h cut, then d psi d pi divided by d x will be equal to plus minus p divided by h cut. So d pi will be equal to plus minus p divided by h cut into dx, taking integration both sides. Integral d pi is equal to integral plus minus p by h cut dx. 1 over h cut is constant, taking common, integral p dx plus minus this d will be cancelled with this, pi will be equal to 1 over h cut integral p dx this is the value of phi x. From imaginary part is 2a prime phi prime plus a into pi double prime is equal to 0. This is, we can write this equation as a square of pi prime whole prime is equal to 0. So this is d by dx into a square pi prime is equal to 0. Both sides multiply dx. We will get 0 into dx. Both sides apply their integration. This will cancel with this integration. So a2 pi prime is equal to c. This will, we will get the constant integration 0 of this will be equal to 0. Integration of 0 dx will be equal to c. So pi prime is equal to a square is equal to c divided by pi prime. Taking square root both sides, c divided by pi prime square root. And we know that phi prime is equal to p by h cut. So we can put c divided by p by h cut square root. This will be h cut divided by p square root into c. H cut c we can replace with another constant b divided by square root p. So psi of x is equal to a into x exponentially power iota phi into x. This is the value of phi of x. This is the value of amplitude c by square root phi prime or p divided by square root p. So put these values in this wave function, psi of x will be equal to c divided by phi prime, and this will be exponential power iota. Phi of x is equal to 1 by h cut integral p dx. So this is the value of wave function. Now we are calculating the approximate solution. So this will be linear combination of two terms. So we apply the probability psi into x mod square. This is the magnitude of the wave function, which is approximately equal to psi into x, psi steric into x. Put the values of psi of x, c by pi prime, exponential power iota 1 by h cut integral p dx dot c divided by square root pi prime exponential power minus iota 1 over h cut integral p dx. So this will be cancelled with this. This will be equal to psi square root. This is pi prime square root. This will be cancelled. C square divided by pi prime if we put the value of pi prime, so we will get the hc square divided by p h cut. So this will be b square divided by p. So psi into x mod square is equal to b square in the constant, and the p square, the p of x. It means that the psi of x, the probability of finding electron is inversely proportional to the classical momentum of the electron. This is inversely proportional to the 1 over px, classical momentum. It means that when the particle energy, the particle velocity is high, the momentum will be high, then the momentum, if the momentum is high, the kinetic energy of that particle will be high. So there will be, if this momentum is high, then the probability of finding electron is less. Probability of finding electron will be low when the classical momentum of the particle is high. If the classical momentum of the particle is low, then the probability of finding electron will be high. This is the classical region calculation. We get the approximate solution for the electron. Thank you so much for watching this video.